All right. Welcome back, guys. Today, uh, let me edit one thing more. Then we will continue. Okay? All right. So today we will understand some concepts, right? So today's goal for us is we will understand the language model, like the fundamental question. Okay, what is a language model, right? So today we are going to understand what a language model actually is. Right? We are not going to start with like transformers and attention and GPU, PyTorch, neural networks. These are like moderate and advanced topics. We have to build our base and understanding of the base. If we have understanding of the base, then we can build like great height buildings, right, and complex things. So instead of these transformers and attentions, what we will do today, we are going to learn very much simpler but basic and the fundamental thing. This will never change. Okay. You know what is counting? Can you count things like 1, 2, 3, 4 like this? 1 plus 1 is 2 like this. If you can subtract, add, multiply, divide, right? If you can count things, you can build a model, guys. You can build a model if you know counting. Okay. So by the end of this today's stream, we will have built a complete like a small tiny language model. What we will use, we will build today a language model using counting plus division, right, and just random sampling. I will explain you what is this random sampling. Just believe it, random sampling, right? And the purpose is simple for today because it is our first day, right? We will not dive into the deep ocean right away. We have to learn like how to swim in a pool, right? So if we understand the simplest possible language model first, right, then when we eventually build our because in this course in this project we will build a 120 million parameter transformer, guys. Can you believe it? 120 million parameters. So we will understand what that huge model is actually trying to learn, right? So over of 10 days, right, we are going to build a mini chat GPT, right, from scratch. And because ChatGPT is like a very big model, right? So we will not build the whole ChatGPT, but we just build a small ChatGPT, which will be fluent in Hindi, English, and one more Indian language like Marathi or any other, right? You can choose your special language, okay? And I will explain every single line for you and every concept, right? Today we will not build any neural network and all something like that. Okay, what we will do, we build a world's simplest language model, right? We will build the simplest language model. We will not use anything, just counting. Okay, if you can count and divide things, you can build a language model, right? And this is important because I don't want to start by showing, oh, you are a transformer, and saying, okay, trust me, this works. Because all things, like maybe some of you knows things, but some of you are like just learning things from start scratch, right? So if you are not familiar with like simple basics, transformer concept can go, you can understand some, but some can go like top of your head, right? So I want us to understand the problem first. Okay, then we will understand why transformers are needed. So we have to understand what is the problem in earlier models, then what transformers solve after this, right? So our plan will be like counting. We need counting, we need tokens, data, then attention, then we will have transformer. Okay, then we will train. This is the whole pipeline. Okay, then fine tuning. Okay, then at the end we will evaluate the model, right? Evaluation. So this will be the pipeline of our project. Okay, and here today we start here at counting. Okay, so today we will go through like what is a language model, what does like autoregressive, right? Like how to find the probabilities, chain rules, logarithms, like perplexity token. So many things we will learn today. Okay, from basics only. So let's start, guys. Again, right? So then again, I didn't answer this question for you. What is a language model? This is a very basic, right? So what is a language model? And what does a language model actually do? Okay, let me like break the ice now about the answer. Okay, a language model just answer this question. Okay, this given a context so far, right, what comes next? This is the just one thing a language model do. We will provide some context to the language model, and then language model tell us what will come next. That's it. This will be our input, and this will be the output of language model. That's it. How big language model you can take? Okay, only thing it do is this. Just tell us what comes next by given the context so far. That's it. For example, let's take a sentence in a language, right? This is very famous in academics, like the cat sat on the. If you know this thing, right? If you know these things, guys, right? what next thing should come here? If you are given this, like the cat sat on the, right, there are several options. The cat sat on the mat, the cat sat on the floor, cat sat on the roof, right? So anything could be there, or like table. So anything could be there, right? Anything, right? Right. This is like most likely outcomes. Like if I say, okay, the cat sat on the Monday. Is this Monday likely? Tuesday, right? Cat sat on the you can say air. This is very likely, less likely outcomes for this place, right? These are the very likely outcomes for this place. So what language model do? Language model find us the most likely outcome for the next place given the context. That's it. What is the most likely outcome? Okay, given the context. We have given this context to a language model. Language model must tell us one of these, right? If language model telling us this, like it feels like it doesn't work what we wanted, it should go with this, right? Because some continuations are more probable than others, right? Our brain also learn patterns from language only, right? Our brain also learn pattern from language, right? Like, okay, go to the school. Ram goes to school. So what most probably sentence we learned in our schools, right? Like this, right? So and give me your pen, give me your shirt. You cannot say, okay, give me your Tuesday, give me your January. This is less probable. If you are more creative, then you can say anything, but most probable patterns are like this. Whatever things you seen the most, right? Then that's how it goes. We will understand everything. You will build the intuition as we go further. Okay. So given a context, language model, what language model do? It just tries to get the next what will becomes next. Okay. So as a mathematics, so as in mathematics, a language model tries to learn, right, those patterns mathematically. Just that's it. Okay. Let me go for this. Okay. Next, token prediction. What is this? Right. Suppose the text is this: I love, right? So this is the context, and model needs to tell us what is the most probable next token, right? Token means I will tell you what is token also, but let's go for it now. So this is one token, let's say this is another token, and we want the third token given these two tokens. So let's say model might assign these probabilities, right? For Python, it goes 2.25. I love machine, it goes like, okay, 0.20 like this. And if you are a CSE student, you will say, okay, I love coding also, right? If you are in AI, in this I love pizza, if you are some foodie or something, 0.10, and I love what do you say, I love workout, like 0.505 like this, and I love what do you say, I love spoons. So it's like very less probable, maybe, right? Like this, 0.0001. So language model can like assign probabilities like this, right? So what should be the real answer, right? Based on the pattern. Okay. So these numbers doesn't matter here. The important idea is we give the previous text. Okay, we give the previous text. It goes to the language model, right? And we got the probability distribution, right? Right? And based on the probability distribution, okay, we don't want first, we don't want second, we want third. Then that should be, we can select this, right? Which probability we want. So what we get? We get the possible next token, right? So the language model is not simply answering, okay, what is the next word, right? It is actually producing something closer, right? It is producing something closer to what the probability of every possible next token. Okay. So Python is not the right answer, or machine is the not probably right answer, but Python is the most probable. Machine is the like second most probable token, right? So this, it distributes the probabilities to the tokens. Okay, that's like one concept is next word prediction. We gave the prediction. Next concept comes in this language model thing, guys, is here. Auto-regressive, right? Auto-regressive, right? Like auto-regressive, if you don't end, it can sound very complicated also, right? But it is a very simple thing. Extremely simple. It means, what is auto-regressive? It means you let me change the color also, right? To this or to this. Okay, we are doing it. It means you predict one token. Okay. After predicting this token, what you do? You add that token, right? You add that token to the context previous. Now it is the part of the context for the model. Okay, it is the input for the model, right? Then based on the including this new updated context, predict the next token again, then add it to the context, right? Then repeat this process. That's it. Predict and add it to the concept, then predict again and repeat. That's the whole loop. Okay, that is the whole loop, guys. For example, what you do, you have this context, right? You have this context, the cat. So what will be the next token you can predict, right? You can predict set, right? Then you have the context, you can have the cat set. What will be the on, right? Then again the cat set on, you have this new context. Now you predict like mat. So this is how this auto-regressive works, right? So context builds up on, right? So the context model, the model uses its previous context, right, to predict the next token. Right? And This process is called auto regressive generation. All right. Auto means self regressive generation, you can say. Like, model keeps using its own previous output as part of the next prediction year, right? Okay, let's give a take an analogy here, right? Let's say, imagine I give you this sentence. Okay, the cat sat on the, right? You have to find this thing. Most of you probably say met, right? Why you probably say met? Because I have been saying this only thing, right? Your brain and my brain have been trained on this pattern only, right? You have seen many language patterns, right? And your brain has learned that pattern. So the cat sat on the mat is much more likely continuation here, right? Uh, then let's say the cat sat on the uh, like moon, right? Or like uh, on the day. So, right? So in very simplified sense, your brain is ranking possible next bets also, right? Based on what? Based on the patterns you see. The much more, the more pattern you see, right? Similar patterns, then the probability of that pattern of you to use increases, right? All right. Right. That was it. So, in a very simplified sense here, your brain is ranking, right, the possible next word also. A language model does very similar, right? Very mathematically similar also. Okay. So this is very important point I will tell you. It will become useful later. Like very important. A language model does not necessarily, right, store facts as facts. Okay. Instead of it what it does, it learns the pattern that allows it to estimate, right? It learns the pattern like this allows the probability of next token given the previous context. Okay. So for example, let's say this is very used example in the academic is like the capital of France is, right? So the model can strongly predict as it is Paris, right? So the model can look like, okay, it knows the geography and all, right? But underneath of it, the model is still performing the next token prediction. Okay. So it is finding the probability of next token given this, okay, context. So maybe Paris has like a 0.98 probability, right? And Delhi has like 0.001 probability, then London, right, then some probability. So Paris has the highest probability. That's why it writes the probability as Paris, right? It does not like that as we know that Paris is the right. It is as fact. We store it, right? It is not, model is not doing that. Model just predicting the next token based on the context. So we might assume like it may look like, right, that it knows facts, but it is not. Language model does not store anything. It just learn patterns, okay? And language model also can be wrong, right? If a language model is very confident, right, does that guarantee that, okay, it is answer is true? There is no guarantee of it, okay? Why? Because high probability of a word does not comply like it is a guaranteed truth, right? Right? High probability does not guarantee it, the truth, right? Like a language model also can assign high probabilities to something that is factually incorrect. This is the one reason language models can be fluent and confidently wrong also. Okay. So, can you tell me, like, is a language model looking up facts, like stored in database? Is a language model looking for that, or predicting likely next word only? Right? Can you tell me? And why does that distinction matter also? So, as you all know, like model is just predicting the next word, next token, right? That means fluency does not automatically guarantee the factual correctness. Okay, if the fact is stored in the database and that is right, if model is fetching the fact from the database, then we can take okay, it's correct. But it is just predicting the next word, right? So if I say okay, capital of India is, if we predict this, it most probably it is New Delhi, right? But uh, if I say okay, capital of India, right, other than Delhi, then what will be the answer, right? It will be Simla or Kolkata or like that, because there were capitals, right? So, no, so the language model is predicting likely next word tokens, right? And now we like look into some mathematics now, which is very important to understand, right? So now we have the intuition, right? And if we have intuition, we can make it mathematical for fact, like to prove things, right? Suppose our sentence contains these tokens, like this is word one word. I am saying word, but it can be token. Token I will tell you what is token. Okay, W1, W2, and W3. Dot Wn, like this. Let's say this is our sentence, and it has n words. Now we want to calculate the probability of entire sentence. Oh, can we do that? Can we find out the probability of the entire sentence? Right? Like this. Probability of W1, W2, Wn. Can we do this? So the problem is that directly modeling every possible sentence is extremely difficult. Okay. Just a minute, I will be back. Alright, let's continue. Right. So, can we model this entire sentence directly? It's very difficult. Like, how can we do that? So, the probability theory gives us a beautiful tool, which is called the chain rule. Right? What is chain rule? Chain rule is to find the probability of the entire sentence here. What we can do is this is equal to probability of word 1 into probability of word 2 given word 1 into probability of word 3 given word 1 and word 2, and so on. Probability of word n given probability of word 1 to word n minus 1. Right? So what does it mean here? What is this? Like orange, okay, here. What is this? This is just the probability of first token. Right? Then this probability of the second token, right, given token 1, right? Okay, this means given. This bar means given, right? Probability of W2 given W1. Okay. Then we have this probability of W3 given W1, W2, right? So the probability of the whole sentence, okay, is the probability of the first token multiplied by the probability of second token given first token, right, and so on, right? And this equation is very, very, very important, like extremely important, because entire language model predicts, okay, entire language model is ultimately about estimating these conditional probabilities. Okay. So the central objective of this is to find the probability of next token, right, given previous tokens. Okay. So this is the core object we are trying to learn. Eventually our transfer will learn something like this. Okay, our transformer will something like this. The probability of xt given x1 x2 dot xt minus 1. Here xt means the current token, and x1 x2 xt minus 1 are like all are the previous tokens. Okay, so wait a minute, I have a call. Hello. OVH. So I am coming downstairs. Okay. Right. Okay, so difficult. So this is chain rule, but why it is very difficult to like model the probability of entire sentence, right? Why is it very difficult? Because if we want to find the probability of a sentence directly, there are multiple complications. Like one is combinatorial, right? Explosion of language, and one next thing is sparsity of data, right? Sparsity of data. Why it is? So vocabulary explosion. Okay, what it is? It is like the number of possible sentences, okay, grows exponentially with sentence length, right? If we have this n length, right? So if a language vocabulary has like if a language has like let's say 100,000, right, unique words, right? A language has these unique words. This is the vocabulary of a language, right? This is the vocab of a language. Now, for a short sentence of only 10 words, like if you have like n is equal to 10 words in a sentence, right? Then the number of word combinations of length 10 based on this vocabulary word, which will be like you have 10 positions to fill. Each positions have 100,000 options, right? So what will be this? It will be this v is equal to what? 100,000, right? So what is the length of vocabulary? To the power 10, right? Which is like 10 to power 50, I think now, because it is 100,000 here, 10 here, right? So 100,000 to power 10 is like 10 to power 50, right? So if we are taking 5 zeros from here, making it 10, right? 10 to power 50 here. So can you put this in perspective? 10 to power 50. The 10 to power 50 is like trillions of times larger than the number of atoms on Earth. Okay, it is impossible to calculate or store the probability of that many combinations. It is impossible to calculate this also, right? What is the probability? Right. And second thing is the data sparsity problem. To estimate a true probability, a model needs to see sentence multiple times in its training data to count its frequency, right? Right. So most valid sentences are entirely unique and will only ever be spoken or written once in a human history, right? So if a model encounters like a perfectly grammatical sentence that wasn't in its training data, right? So a direct calculation would assign it to a probability of 0, right? Because there is like let's say we have 100 sentence possible, right? Possible sentence. This sentence and 101th sentence was not in the vocabulary, right, or in the combinations. Then what is the probability of this sentence? Probability of this sentence 101 given the 100 sentence, right? It is 0 only. This means the model cannot generalize to understand new, creative, or slightly altered thoughts, right? If it is exact fitting, like I know Ram and I knew Ram. Let's say models already seen this data in training, but it does not seen this. So it cannot assign the probability to this word in this sentence. It will be zero probability for this. Okay. And next thing is context long dependencies. Context and long distance dependencies, right? So okay, right. So the meaning of this, like meaning and the probability of a word often depend on words that appeared much earlier in the sentence, right? Like, let's say you have this sentence, right? Like the books that I left at my friend's house last week were heavy. Let's see. So the probability of the word heavy here depends heavily on the word books. Okay, from the 11th from 11 words ago, right? So directly tracking every possible permutation of these long distance relationship require taking a in like intractable amount of historical context, right? So that's why these problems, context of long distance dependency and this the explosion of the vocabulary, right? These problems were there, and sparsity of data also, which will assign the probability 0 in that case, right? So that is why we need like chain rule and Markov assumptions like n-grams. We will learn this also, n-grams and all. Okay, neural networks, transformers. That's all, right? Okay, so yeah, like and you understand the chain rule also, Alright, let's take a numerical example also to understand this. Okay, let's use this. You have this I love LME, or you can do anything, right? So suppose I, probability of I is, let's say, like probability of I is 0.1, and probability of love given I is 0.05, let's say, and probability of LMA given I love is 0.2, right? Then what will be the probability of this entire sentence, right? Then probability of entire sentence would be probability of I, which is 0.1, into probability of love given probability of I, which is 0.05, into probability of LMA given I love 0.2, right? So this will become like, what is this? It is 0.005. If we do this, it will become 0.001 overall, right? So probability of the sentence I love LMA is 0.001. Again, so these numbers are only an example here, right? The important part is how the chain rule decomposes the probability. We are just explaining this for now. Okay. Now we use log probabilities for this. Why we use these log probabilities? So there is a numerical problem with multiplying probabilities. Okay, very interesting numerical problem. When we multiply probabilities, suppose we have like let's say, suppose we have 1000 tokens, right? So maybe every token has probability of 0.01. Let's say all tokens have equal probabilities, right? Then what will be the probability of sentence, right? Probability of sentence like 0.01 to 0.01, right? 1000 times, right? So that is like 0.01 to power 1000, right? So it will be like similar to 10 to power minus 2000, right? So that is an incredibly tiny number, very low number, right? At this number, computers can eventually underflow or represent it at 0 also, right? Computers can like underflow in that case, right? So when we are multiplying the probability here, and the probability of all the numbers is very, very, very small, all the tokens, right? Then the computers can fail in that case, right? So instead of multiplying probabilities, we can take logarithms, right? So you know this formula already. Log of A cross B is log of A into log of B, right? Right, you know that. So therefore the log of probability of sentence will be log of word probability of word 1 plus log of probability of word 2 given word 1, right, plus log of probability of word n given 1 to n minus 1, right? So from multiplication, if we apply log, then it is converted to addition, and this is very much numerically stable also. Okay, and this will matter later for us also, right? Remember this, because later when we train the neural network, right, our cross entropy loss will be directly connected to these log probabilities. Okay, so don't take it lightly. Remember this log probability, how we using. Okay, so today's sentence probability is like log probability, right? But later what we will do, we will understand the log probability. From log probability we will go to negative log likelihood, then we will go cross entropy loss, we will go back propagation, update model parameters, right? So this is the just a bridge from day 1 mathematics to day 7 training. Okay, now understand one more thing. Okay, next thing is, guys, uh, next thing is perplexity. What is this? Okay, what is perplexity? So you will heard this word very much throughout this project, okay, which is called the perplexity. Okay. Let me write it again. Perplexity. So just perplexity is basically just a measure of how surprised the model is by the actual next token. What does that mean? Okay. Like very simple here. How surprised the model is by the actual next token. Okay, so lower is better also. This is very interesting thing here. You see, lower is better. Okay. Okay, rough intuition is like, okay, if perplexity is 30, right? Okay, let's say perplexity is 30, let's say. That means the model is behaving roughly like it is choosing between about 30 equally likely possibilities on average, right? We will formally derive perplexity later, but you can see, like, if I say, okay, if I have perplexity is 5, so this 5 means model is predicting, and or you can say choosing, right? Model is choosing the next token from 5 tokens available which has like similar probabilities for the next token. Okay, like let's say the cat sat on. We have like mat, floor, table, right? Like it has probability 0.3, 0.3, 0.29, right? And other words. So here perplexity could be 3, right? Because it is choosing, model is choosing, like, and it answers the match, choosing the 3 from, choosing the next token from 3 most likely next tokens, right? So here the perplexity is 3. Now the lower is better because the model is not confused, right? Model is not confused here, right? So lower perplexity means model is less surprised and better predictions will be there. Okay. All right. Let me test you one thing. If I like, okay, tell me one thing. Okay, guys, tell me one thing. Like, if I multiply 1000 probabilities together on a computer, what can go wrong? Right? I already told you. If I multiply 100 or 1000, 10,000 probabilities together on a computer, what can go wrong? Can you tell me? The answer here is uh, the number can become so tiny that it underflows to zero. Okay, and what is the solution for that now? Okay, solution for this is use logarithms. Okay, now let's understand, guys, what is a token. Very important. Okay, I have been keep saying it, right? We keep saying token, but what actually is token? Okay, and which is very interesting part of the pipeline of AI models. Okay, token. The formal definition for could be like, okay, the unit of text that the model reads and predicts. Okay, unit of text that model reads and predict. That is token. Like, a token can be character, it can be a word, it can be a subword, right? It can be a character, it can be a word also, it can be a subword, right? For example, we have character tokens, right? Like C, A, T, these are the character tokens. And word token is like character token. And we have word token also, right? Like CAT, cat, mat, read, like this, right? And subword token, these are like subword token is like un plus believe then able, right? Like this, we break the longer words in subwords, right? Why we need token? Why we just can't use words, right? That's important. Why we just can't use words? Why need token? There are three major problems. Okay. Problems using only words. There are some problems, which is problem one is vocabulary explosion. Okay, so you have, like, consider you have words like this. Okay, play, plays, played, right? Playing, everything, player, right? So if every variation is treated as a completely separate word here, right, the vocabulary becomes very huge. Okay. So vocabulary explodes. So we will it will be hard to assign probabilities to the sentences, right? And next problem is problem 2 is the rare or new words. Okay. Let's say, suppose the model sees this word, bhasa verse. Suppose model sees this word, right? But that word was never in its vocabulary. Okay, it was never. It never sees that word. Okay, so a traditional word label system may produce this, like unknown, UNK. So like unknown token, right? Like information is lost, right? Now, if like vocabulary, this word does not exist in the vocabulary, and word label system produce this unknown there, then this word is lost, right? Word is lost. Model was not able to count this, right? That's the problem. Okay. Next problem is, everything will be explained in detail also, okay? Problem 3. Other languages. As we are building a multilingual project, right? Right? Our project is multilingual, like it has English, it has Hindi, it has Marathi, right? Hindi and Marathi use the Devanagari heavily, right? They use Devanagari heavily. For example, you have a word Sundarta, right? It can be understood as pieces related to like Sundar plus Ta, right? So subword tokenization can be capture recurring pieces. Okay. This is useful because one tokenizer can represent many different words. Okay. Without requiring every complete word to be in the vocabulary. So if this has it has Sundar plus Ta in vocabulary, then we don't need Sundarta as a special like additional word in the vocabulary, right? These both can make Sundarta, right? So our day one simplification is this, like today we will intentionally use words as a token. Why? Because if I introduce byte pair encoder right now to you, right? we will lose the main idea. Okay, so today we just use words as tokens. Okay, and tomorrow we will build a real subword tokenizer. Okay, on day 2 we will actually train the tokenizer for our project. Okay, I have a question for you. Like our project will mix Hindi, English, and Marathi, right? In one model. So why our subword tokenizer is better fit than the whole word tokens, right? So for answer for this is like it will have a smaller vocabulary when we use subwords, right? And it is better. It will handle better the rare words or new words because it can split those words and we can find like similar words from those splitted words, right? And reusable pieces will be there to like two tokens, subword tokens can make a real word, right? Better fit for multilingual text. Okay. Okay. Today we will build our first language model by hand, scratch. Okay. It will be a bigram model. Bigram model. Okay. Like we are finally going to build a language model here, but this first model will be extremely simple. Okay. It will be a bigram language model, as I say. So what is a bigram? Bigram means two consecutive tokens. Two consecutive tokens. For example, I love is a bigram. Is a bigram here. Alright. So is love LMA. It's also a bigram. And when we end the sentence with this, like LMA, and we have end sentence character, right? It's also a bigram. Okay. So what a bigram model do? A bigram model makes one very simplifying assumption. Okay. Bigram model assumes the next word depends only on the previous word. Okay. Mathematically, like probability of Wi given W1 dot Wi minus 1 equal to probability of Wi given probability of Wi minus 1. This is how this assumptions takes place, right? Like instead of looking at the entire previous sentence, right? We only look at the immediately previous sentence token, right? This is the first order Markov assumption. This is called the first order Markov assumption, right? This assumption is very wrong for real language, but it is perfect for teaching, right? Because we can calculate everything by hand here, right? Okay. So let's say this is our training corpus, okay? Here, and training corpus, right? Let's say our training corpus contains only these sentences. One is this sentence: I love LMA, right? Second sentence is I love NLP, right? And third sentence is I code LMA, let's say, right? LMA. What is this S? This S is just start of sentence, right? And this is end of sentence, right? These are special tokens. Special tokens, right? It is not word token, it is not subword tokens. These are the special tokens. It will be always there, okay? So we have to count the bigrams now, okay? So we will go. So it is a bigram model, right? So we have to count the bigrams, right? So token by token, right? We will go token. So let's first take the first sentence. First sentence is here. S I love LMA, right? This is first our bigram. This is first token, second token. So first diagram is this. Here, then we have I love. Then we have right. Similarly for second sentence, then third sentence, right? For second sentence, we have this I and I love. Then we have love NLP and NLP to this. And third sentence is like same. Here I, then I code LMA, then LMA is the end of the sentence, right? Now we can count them, right? I am just counting it. Count of this is let me build a table also, right? Previous, and this is the next token, is a count. Okay. Previous is est, next is I. How many are these? 3. I love is 2 and I code is 1. Love LMA is 1. Love NLP is 1. Code LMA is 1 and NLP 2. No, this is 1 and LMA and this is 2, right? So we have these diagrams, guys. Are you confused now? Are you confused? I thought so. You can confuse. So what are we doing, right? All right. Right. So let's understand again. We have these three sentences. Was the diagram and what is the language model? Language model is it assigns probabilities to the next token given the previous token, previous context. What is previous context? Here we have these sentences right in the training set, right? So when we say, okay, I have this much context, give me the probability of LME, right? I have this much context and give me the probability of LME, right? Here, I love LME. I have this much context. Now, what does LMA will treat look like, right? Okay, probability of LMA given context, right? Okay. What it will be? It will be from the conditional probability, right? Probability of LMA comma context, right? Upon probability of context, right? Now probability of all of this sentence, right? What is this? Where will we find this whole probability? I love LMA, right? We can find this from the chain rule, right? So we have to find this probability of I love LMA is like probability of I into probability of love given I into probability of LMA given I love, right? So that's where we have found this, right? So probability of LMA given I love is this, probability of this, probability of I into probability of love given I, right? And where do we find this probability? Where do we find this? We found this probability of I love and probability of I. Where we find this probability of I love? We found from the vocabulary or the sentence formation, right here. Okay. So what we can do? These are the bigrams. We can count these bigrams. We have counted those bigrams. Now we can convert these counts into probabilities. Okay. So probability of next given previous, right, is equal to number of count previous and next upon count of previous, right? So this is our context here, or let's say these are the sentences stored in our bigram model, right? Okay. So whatever the context we have in the corpus, we transform that and convert in when we are trying to convert the bigram model, right? We make the bigrams and count those bigrams, right? Based on those bigrams, we find the probabilities. Okay, this is in our storage, right? This is in our storage. We can count those. So what we can do now, probability of love given I, right? Probability of love given I is, because we saw I love, right? And I love, I code. So I has 3 outgoing transitions here, right? Therefore, probability of love given I would be uh, count previous I love are 3, 2 times, right? And total I are 3, right? So total number of times I we saw was 3, right? So it is 2 by 3 here, and it will be become probability 0.667. So probability of love given I would be point of 1 by 3 or 2 by 3, I think. Yeah, 2 by 3, right? Approximately 0.67, right? Similarly, if we find the probability of LMA given love, right? So what would be probability of love LMA on probability of love? We can say count and count, right? So what it is? LMA, love LMA, how many times? Love LMA, it is 1 time. I love, it is like this, okay. 1 time it is, and love, how many times? Love 1, 2 times, right? No, I love here, love LMA, love NLP 2 times, right? So it is 1 by 2, right? 1 by 2 is 0.5 probability of this, okay. Okay, so right, next thing, find the probability of, let's say, this is very important, okay, probability of code given I. So it is like probability of I code given count, given count of I, it will be 1 by 3, right? It's like 0.33, right? So if you sum them up, right, this is very important. 0.67 plus 0.33 is equal to 1. How important this sentence could be, guys, for us? So write this in your notes. For a given previous token or the context, okay, the probabilities of all possible next tokens should sum to 1, approximately 1. So you can see there are only 2 possible things from after I. After I is love, I code, right? There is 2 possible. So sum of these 2, love and code, is approximately 1, right? Right? हेलो, हाँ जी, No, 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 no. See, all right. Here. And next thing, so you know how it predicting text and all, right? Next problem here. Now imagine we want our model to generate a sentence. Okay, we want our model to generate a sentence because all of these models are generative models, right? All of these models are generative models. So let's say we want to start from this S, right? What will come next? Only I, because everything is only I is possible. So probability of I after S is 1, right? So now we are at I, right? After I, possible next token could be like love has probability of love given I is 0.67. Probability of code given I is 0.33, right? So the model samples one of them, right? So suppose it chooses the love, right? Now after love, now we have this, right? From love, so possible next token are like LMA and NLP, and both have similar properties. LMA is 0.50 after love, right? And NLP also have this probability only. Suppose it chooses LMA, right? And from LMA, probability of end is 1, right? End of sentence, the special token. So now generated sentence is I love LMA, guys, right? So score is sentence now. Now let's calculate this, okay? Probability of I love LMA, right? And complete sequence is this. So therefore, or say I code LMA, right? So probability of I code LMA would be like this. Probability of I given starting sequence into probability of code given I, probability of LMA given code into probability of end of sentence given LMA, right? And from our table, probability of I is 1 here, right? And probability of this is 1 by 3, and LMA code is 1, and this is 1. So therefore, probability of this sentence is 1 by 3. Okay. So as you can see, guys, this is a complete language model for us. So right, what we did, we counted things, then we divided, like to find the probabilities, right? And then sampled, like whatever the next token would be, it generated the text, right? So next 9 days are essentially about making the estimate of next token given the context, right? Okay. Okay. Let's understand one problem. Okay. What will be the probability of NLP given code, right? And we never see code NLP, right? In our bigram, right? We never see it. Like, did we see it code NLP here? No, never. Code LMA is there, but not code NLP, right? So where is code NLP? So it will be like this: probability of code NLP given probability of code, or we can say count, right? Count of this, and it will be like this will be 0 count, and this is some code like 1 count. The probability is 0, right? So now imagine I say what is the probability I code NLP, which is 0, right? Therefore probability of this sentence is 0, right? So if I want to see this, right, probability of starting and end, it will be 1, then I code is 0.1/3 is there, right? Code NLP 0, and this is also 1. It is making probability 0. So one unseen pair, right? Only one unseen pair destroyed the probability of entire sentence here, right? That is the 0 probability problem, right? This is our 0 probability problem. Okay. To solve this, we have a solution called smoothing. Okay. So the classic solution is just add one smoothing. Okay. Add one smoothing. Formula is like probability of next given previous is equal to count of previous plus next plus 1 upon count of previous plus v. Why v? V is the vocab size. Okay. So the idea is pretend that every possible pair occurred at least once. At least once is there. Okay. So this is why we are adding one here. We are assuming this. Whatever new sentence we are getting, we are assuming that we have seen the sentence at least once, right? Right. So for example, we have this count code common LP 0 here, right? What we can do is we can make it plus 1, and what right? So the probability becomes small, right? But it is non-zero at least, right? And vocabulary size is 7 for us. Like unique words we have are 7 only, right? So 1 plus 7 is there. It will be 1/8 now, right? So probability of this is 0.125. Okay. So without smoothing, the probability was 0. With smoothing, it's 0.125, right? So smoothing fixes the immediate 0 problem, right? Here, but it does not solve the fundamental problem of generalization, right? This is why we need neural networks. Okay. This is, we are using 2 grams here, right? We can use 5 grams, 10 grams and all, right? Okay, so we are using 2 grams here, right? We also can use like 5 grams, something like that, right? Like previous 4 sentence, right? If diagrams only remembers one previous word, right? So why don't we just use 5 previous words also, if it can have like more good context for probability, right? So suppose our vocabulary size is, let's say, 32,000 unique words are there, right? And if we take 5 gram table can require up to v to power 5, right? 32,000 to power 5 entries, right? That is like the so it is like approximately 3.4 into 10 to power 22, right? These are the possible combinations here, right? So this is enormous here, right? So problem is, if we have more context, right, and more possible combinations will be there, right? That will make it a huge table, all right? Huge table, and it will lead us to the data sparsity again. Data sparsity, and so counting does not scale here. No scale, because most of the words will be unique, and counting will be not there, right? And the count will become 0. Okay. Now that's why we have to like limit it somewhere, right? Like 4 grams, 3 grams, 4 grams we can take, but 5 grams is way too much. Okay. Now the real thing, we will start implementing it our day 1 now, right? Here, and here this is, I have created a solo project here, folder, and it is Okay, let's create a new file here. Okay, in gram, right? Now rename it ngram demo.py. Okay, before that, what we have to do, guys, we are in the solo project, right? We have to create a like separate virtual environment for this, right? For this project, we do this for every Python project. Okay, now in this, what we will do is Python m like module, we can say, right? And virtual environment, we can take say it like as like we can give it any name, like LMA environment, right? Python did not found. Okay, let me do Python 3 env LMA env, right? Okay, so you see this LMA environment is created with Python. So what we will do everything, right? And we will activate this environment, right? With this script, we have this activity script. We have to run this. So source, okay, source. Oh, it's LMA, LAM. Wow. I can rename this, right? And I can make this LMA. Okay, LMA environment bin activate, right? Okay, sudo remove LMA. Can we do this? Remove LMA env. Okay. Okay, so let me okay, first let me deactivate this environment. Okay, make it activate, right? It is deactivated. I can remove this ref LMA env, right? It's gone, right? And I will create this again here. Python 3 MVEN virtual environment LMA VENV. It's created. I will activate it now. Source LMA no MA VEN. Okay, env bin private, right? As you can see here, guys, what was the m there, and that was so that m flag stands for module name. Okay, so it tells Python to run a built-in library module as a standalone script. Okay, okay, in your Python command 3 it is here, this Python 3, okay, this, okay, Python 3 mvenv here, right? It tells Python to look inside its own standard library, locate the venv tooling and execute it to build your folder, right? So why would we need this virtual environment, guys? A virtual environment is a like isolated workspace, right, on your computer. Here is like it prevents conflicts also. Like project A might need like Django of version 3.0 and project B needs Django 5.0, right? So venv keeps their packages completely separate, right? And it also keeps it prevents you from cluttering and breaking your Ubuntu operating system code Python installation, right? So, and easy sharing, like you can save your package list to a text file and free. Okay, okay. So if I run this command here, okay, let me tell you, if I run this command which Python, so you see it is using this Python here, right, in this virtual environment. But if I deactivate it and now I ask which Python or which Python 3, you see it's the local Python I have in my system. So when I activate this environment, it points to the Python which is local to this project. Okay, okay. So that's why we need this, right? So the system is no longer using Ubuntu global Python, right? And if I see ask it, okay, what is my PIP list, right? You see package version and PIP 24. This is very empty list, right? So there is no packages there installed, right? And I can install some packages, then I can show you okay, if I go like deactivate it and if I do PIP list, you see how many packages are in my local system, right? These many packages, AWS, I don't know what is they're doing there, Jupyter, and these many packages are there, right, in my local system. But in this system there is not many, right? I will install packages, so anything I will install from now on, PIP will point to this environment only. Okay, this will be the path. And I will create our file now. Okay, before that I need to install something for which will be used in this file. Okay, So I need to install PyTorch, tokenizers, sentence piece, NumPy, okay. TQDM, like TQDM is like I will tell you what it is, okay. And data sets. So it will be pip install torch. It will be PyTorch, right? Tokenizers, right? Sentence piece, and I will need NumPy also, and I will need TQDM, and I'll need data sets, okay. Alright, so it's installing, guys. Till then we will import some things, okay. We will try building our file. First thing is we will import random, okay. What is this? So it's a Python standard library module, okay, for random operations, right? Why we are importing this? Because our language model does not always have only one possible next word, right? For example, it can have love and quote for given I and I. We have already seen it, right? With different probabilities. So we want to sample according to these probabilities, right? So we want this. Next we will import from collections import default text and counter. What it is? So Python has a module called collections, right? In this collections module, we use two useful packages, which is one is default dictionary and counter. Okay, counter is useful for counting, as you can refer from the name only, right? And default dictionary allows us to automatically create a dictionary entry when we need one, okay. So okay, then it is our training data. It's like it's our corpus, right, is equal to this. One is I love LMA, right? Then we have I love. I am using the same example from the okay. So we have very less space, guys, because of the okay, like it can where I can empty my space, right? Where I can do it one thing, one place I know. One place I know is there it is. Right. Okay, and we have this objects. What's the name? Alright, I think I solved the problem of low disk here, and I am creating the corpus as an LP here, and I code LMA, right? You can see here. This is our list. So what is this corpus? This corpus is a collection of text used for training in the in this. Okay. So this is our corpus open. Now here our corpus has only 3 sentences, right? But in real project we will eventually have our English data, Hindi data, Marathi data, all of it. Okay. But the fundamental idea remains will be the same, like text. From text we will get the tokens. From tokens we get the patterns and then model. Okay. So special tokens will be there. Okay. Like we can define BOS equal to S, or we can say S, right? Like beginning of sentence, right? Why we need it? Because imagine like I have this I love LM here and all. Okay, how does the model know what comes before I, right? So we introduce this special character. So sentence will become this special character, then I love LMA, right? So we have used in this training, right? You understand it. Next we have EOS equal to end of training, right? End of sentence. So because generation needs to know when to stop also, right? So when it is continue generating, when it encounter this end of sentence, then it will stop generating. Okay. And what we will have, we will define a token function which is tokenize. Okay. And it will take a sentence, right? Sentence like a string of a sentence, right? Or we can type enter it also, like str, right? It will be take a sentence of type str, and we are defining a Python function here, right? So it will take a input sentence as input. So its job is to convert raw text into the tokens. Okay. So we can say about it like through Docker strings, like it turns a sentence string into a list of tokens, right? And wrapped in S, right? Because model works on a sequence, right, of tokens, not on raw string. Right. That's it about this function. And so to define any function we can do this always. Okay. And now, so this also explain us the conceptual region, right? That our language model does not directly operate on complete string, right? I love LMA like that. So it operates on tokens, right? So what it will do, it will return BOS, right, plus sentence dot split plus EOS, right, end of sentence. What is this doing, guys? Let's break a sentence. Our sentence is this: like I love LMA, right? Then we call this on sentence dot split function, right? What it will do, it will produce a list of this sentences I love LMA, right? This is our sentence. If I run the split function on this, it will give us list of tokens I love, because we are using the word tokenizer, right? For now, I love LMA, like this. Okay. Then we have BOS, which is this. It will add in this, right? It will be concatenated list. So final list would be this. Final list would be this, like this. And I love LMA, right? Like this. So this is our token sequence. Now what we will do, we will have our next function, right? Def train by gram. Okay, we will take the corpus. Corpus is a list, right? Here. Now this function receives the corpus and learns the bigram counts also. Okay. So important idea is like here training is just counting. Okay, at least for this toy model, right? Just we need to count. So counts is equal to default dictionary counter. Okay. So what we are doing here is this creates our nested count table. Okay. Let me explain this. Conceptually, we want this. Counts is like we have this S starting. From S we have I, right? This is 3 times, right? From I we are going to love, which is 2 times, and code, which is 1 time, right? From love we have LMA, because we are training the bigram, right? And we have NLP 1, and so on, right? So mathematically this represents the count, right? Count previous comma next, right? So for sentence in corpus, right? Let me do it. For sentence in corpus plus no. Right, we are picking the sentence from the corpus. So we will take each sentence one by one, training corpus one at a time, right? First we will have I love LMA, then I love NLP, then I love I code LMA. So this is for loop for us, right? Now in this tokens is equal to we will call this function tokenize sentence, right? Here. So we convert this sentence into tokens, right? In this here, like this. First sentence will be like this. We will get this list. Okay, these are our tokens. No. This is very important. For previous comma next in zip tokens comma tokens 1 here. What is this? Okay. Alright, so alright, so that is here. So this is looks complicated also, right? So explain it let's understand this. Suppose let's go here. Suppose our tokens is like this, right? This is our tokens, right? Okay, now this is our tokens is equal to this, right? Then so tokens 1 is equal to this. It will leave this and it will contain only I love LMA, right? Like this. Okay. And now it will zip pairs them. Okay. Now zip will pair them. So zip will pair them. Okay, like this. Like this. S comma I, right? And I will with love like this, and love with comma LMA, right? It will exactly the diagram we calculated by hand. Okay, so you see, first we take the from tokens, we took the first one, right? Then it was zipped. So then we will have this counts previous, right, comma next plus is equal to 1, right? What is this like? You understand how it was working? Because we have the tokens, right? Tokens is like this. S I love LME, and we have this. Then tokens 1 was this. I love LMA and S, right? You see, these this will become pair. Okay, they are becoming the pairs. So si will become pair, this will become pair, this will become pair. Zip will make them pair. Okay, we are zipping this right here. Okay, so whatever pair we get, one will be the previous, one will be the next, right? Like this. This can be the previous, this can be the next. So previous comma next, here it will be our plus will increase, right? Right? This pair will increase, and with this will be our count also, right? We can do this now. Return counts, right? This is how can we do this. Alright, and also if you want to learn like say about this thing, like it will learn the model by counting, right? Which word follows, right? Which one, right? So because probability of next given previous, right, is estimated as count of previous comma next given count of the previous, right? Like this. So it will return the nested dictionary called counts, right? We can also return the nested dictionary counts, right? Where counts previous next is equal to the how many times that pair was seen, right? You understand this now, right? So this is just a nested dictionary we will have, right? So, and this default dictionary counter means like if we ask for some word, right, count some word inside this, and it does not exist there, right? So what it will, Python will auto creates an empty counter, okay, a counting dictionary, right? And this saves from writing if not in the dictionary checks everywhere, right? This will save us from that, and yeah. Now next thing will be for us will be, we will turn these counts into probabilities, right? Okay, so we'll define a function probability, right? It will take counts dictionary and previous comma next, alright? And here what it will do, it will tell us probability of next given previous, right? Equal to count of previous comma next, right, given count of previous, right? So that's it. So total after previous is equal to sum of counts previous, right? Values. So what it will do is it will take, okay, how often previous one occurred, okay, so it will take counts and tell us how often it has occurred, right? In this, I think I removed, yes, so here I occurred 1, 2 and 3 values. How many values are there? 2 and 1, right? So 3 times I occurred, right? Like this. So we can count previous from like that. And next thing is right, and next thing is if total after previous is equal to 0, right, then what it will do, it will return 0.0, right, else it will return counts previous comma next value, right, next divided by total previous, right, then we will have our print table function, print probability table here, and counts again. What it will do, it will print every learned condition, right, conditional probability, right, probability here, right, okay. So what it will do is it will print, okay, learned probabilities, right, and we will can do in here. And next thing is for print and counts, right, for next comma C in counts print dot items. This is how we access dictionaries, guys, right? So as you can see here, we are checking the first dimensional keys, then in this we are checking the next dimensional keys, okay. So previous, next item, this will be the key and this will be the value for it, okay. Key and value we are taking, and here P is equal to probability of counts we are passing, and previous and next we are saying, right, we are saying there, and we are printing, okay, print f string is p of xt is 5, right, here prev less than 5 here is equal to P pointed to F, right? C, okay, times, right? So you see, like we are printing like so this will print the probability in a readable format for us, okay? And next thing what we can do, guys, is we can define a new function here, okay, called to generate a new sentence, right? Generate, it will have counts, max length equal to 20, right? What it will do is it will produce a new sentence for us, right? By repeatedly sampling the next word for us, right? So this is the auto-regressive generation, right? We predict a token and append it, right? This is auto-regressive generation, right? Okay. Now what we have current. What we have current is BOS for us, right? And output is empty for now, right? So start a context in the beginning of the sentence token, right? And this output is, it will be collected words go here, right? So what we will do, we will go for in range of max length, right? So it is just for safety, okay? Like it's just set gap, so we never loop forever, right? Here. Next words equal to counts based on the current, right? If not, next words is not there, then break, right? So here we are using underscore only because we just don't care about the loop counter here. There is no name for that, right? Okay, and so next word, so it will ask, okay, given the current token, what token will come next, okay? So this will give us a dictionary also, right? So it will, if current word is I, right? This will give us love and code, right? Next, if next word is not there, if there is no possible next token stop in that case, right? Now words is equal to list of next words dot keys, okay? Here we are extracting the candidate words, like for, if let's say our previous word was current word is I, then we get like love and code, right? So these are the we get love and code here, right? And then we convert them into list format, right? Next we have this weights is equal to list of next word dot values, right? Then for this we get here we can see for I we have 2 and 1 in this case, right? Right? And now is the most important generation, okay? So random dot choices will be what it is like. Let me do is current is equal to random dot choices, right? From the words, comma weights, right? Is equal to weights, comma k is equal to 1, okay, 0. What is this? Okay. So this random dot choices will pick one word, okay, with probability proportional to weights, right? So weights probability proportional to weight, and so love weight is 2 is twice as likely as code, right? So which the code weight is 1. So this is literally sampling from p dot next current here, okay. So love is twice as likely to be selected as code. So this is effectively a sampling like probability of love given I is 2 by 3 here, and probability of code given I is 1 by 3. So this is auto-regressive generation, right? And okay, so what it will return the one size array from this, okay. Like if we want two words from this, we can give 2, but we want just 1, and 0 is, it will take the first element from that, right? And next thing is we have this if current is equal to current is equal to end of a sentence, right? Then what will we do? We will break, right? And output dot append current, and at the end we will return things, right? We will return dot join output, okay. So what it will do, it will join the word list back into a sentence string, okay. So it will make this like a list. This is the list, output is list, like it will make it a string, okay. Alright, then we can score a sentence also, right? Define score sentence here, right? From this counts, comma sentence. We have count, so what we can do is it will compute probability of sentence, right? Using the chain rule, right? And this is exactly, let me write it also, right? This is exactly how we will later measure a model with perplexity. Okay, so that's it. Then thing is like, okay, what are the tokens? Tokenized sentence, right? Whatever sentence we have. Then probability is equal to 1.0, right? Here, and for previous comma next and zip tokens, we will first pair them, right? Tokens one this like this, right? From here what we will have, step equal to probability of counts comma previous comma next, right? Like this we will get the probability of this, and p asterisk is equal to step of the entire the return p. This is a probability of the in real world we add the log probabilities instead of the multiplying, right? So just to avoid underflow, see Day01, like, okay, alright, alright. Then what we will do is we will define our main function now. Okay, here random dot seed 0. So here we are just so random generation normally produces different results every time, right? Here why we are fixing the seeds because it is 0. So we make the demonstration reproducible here, right? So this is useful here. Next is we will print something like training corpus like this for S in corpus print like this comma S here, right? Then next thing is counts is equal to train diagram called COU like this, right? It will learn the counting, okay? It will build the count table and print probability table here from counts, right? And next thing we can generate some sentence, okay? Print like generate sentences, right? The model writing on its own here, right? Okay, and here for I in range of 5, right? Print f I plus 1, right? Generate counts, right? Okay. Next thing what we can do is test is equal to I code LMA. Okay, then print is in value of test, right? Here. Okay, right? This is equal to whatever. Okay, equal to this code sentence, right? We can counts from a test, right? From 3f right? And what we will do is compare this to the font 033. We computed by hand in the script, right? Computed already by hand, right? Then at the end what we will have is if main is equal to main, right? Okay, whatever main is this, right? Whatever. No, it's not like that. Source LMAVENV will TWH we have this now. Okay. So why we are using this? Like this explains that Python files can be executed or imported also, right? So this condition means if I directly run this Python and programs.py, right, then execute this main py. But if another Python file imports it, then it will not automatically run. Okay. Okay, should I run this, right? Python ngram demo.py, right? What happened? Here. I think our installation was left right, so I think I need to install that. Okay, first all the packages, right? Then it can be supported, I think. Why it is not supported, guys? Hmm? Okay, so I think there is a problem in this. Here, okay, real comma. Next, right? We need this also, right? Because we didn't define it here. So clearly it is real what? It is 0 already. So okay, one error I found here is, guys, one is this in trend diagram. It should be trend next year, right? And also in probability, it's also next, like this. Okay. And one more thing is it's key to keys. Okay. Alright, then we have this, and we can run this again here, right? You can see. So I love LMA, I love NLP, I code. These are the purpose to learn probabilities are this. This is for one. You can see every probability is there, and I code LMA. So generated sentences like this: I code LMA, I love NLP, I love NLP, I code LMA, I code LMA. Right? Probability of I code LMA 0 here. Why it is? But we had this already, right? So it is not fixing like this, right? Probability is getting a very mismatch. So we can fix that, guys. Thank you so much for watching, and we will meet you in the next lecture. We will fix it later. Tomorrow we will meet you tomorrow, right? Thank you so much.